In this lesson, we're going to learn how to integrate functions that happen to be compositions of functions, or rather functions inside of functions. And in order to do so, there's two different methods. The first of which is pattern recognition. You're just looking for a particular pattern to show up inside of the integral, and if you see that, then we're going to follow the process using that method. We could also do an actual change of variables, which we refer to as substitution, to change the function into another variable to make the integral look easier. So I'd like to first of all start off with the recollection of the chain rule. Remember that the only time we ever used the chain rule was when we were differentiating a function inside of another function. And the way that we did that, remember, was by simply differentiating the outer function by keeping the inside function intact, and then we multiplied by the additional derivative of the inside function. So that must mean if we're trying to find an antiderivative, that form should have to show up in order to go back to the original composition. In other words, we need to recognize that there is some composition function that we're trying to integrate, but the derivative of that inside function happens to be attached. And that's a necessary criteria for integrating composition functions, is that we need to also see the derivative of that inside function. And if we don't, we may have to apply a different method. So let's take a look at an example here of a composition function that we're trying to integrate. But it also looks like it's a product of two functions. But the more important thing to recognize here is that we have an inside function, x squared plus 1 is inside of this function. And the derivative of x squared plus 1 happens to be 2x. And so that's the g prime of x that needs to be attached in order to go backwards, in order to integrate that function. So if this is g prime of x and the inside function is g of x, that must mean that the outside function, referred to as f of g of x, is simply x squared plus 1 to the power of 4. Or in other words, this function to the fourth power. So I like to rewrite this in the actual form that it shows up here. I like to write the composition function first, and then hopefully the derivative of that inside function I'm going to multiply second. So I'm going to rewrite this as x squared plus 1 to the fourth, which is our f of g of x. And then we'll write our 2x dx, which is our g prime of x dx. So what do we do in order to integrate this function? Well, it says once we recognize that the derivative of that function is attached, that derivative never shows up in the answer again. So I could really disregard that g prime of x at this point, recognizing that it had to be there, but once it's there, it says now just keep the inside function g of x intact, but now just change f prime back into f, which means find the antiderivative of the outer function. So since this outside function is something to the power of 4, the antiderivative is 1/5 times that function to the power of 5, of course, plus c. So if we started with an f of g of x, then that must mean that this must be big F of g of x. So in other words, if we were to do this same problem using substitution, I would literally be changing all of my g of x's into u, and then I would find du, which is g prime of x dx. It would be the derivative of g of x. So I can now just recognize that if I write it as f of u times du, that should equal big F of u plus c. So the benefit of doing substitution, which we'll see in an example here, is to change the function into some form that looks a little bit easier. So let's just keep on with the pattern recognition part of this process. We should recognize that if we see a composition function, f indicates the outside function, while g of x indicates the inside function. G prime of x dx is simply going to describe the derivative of that inside function that needs to be part of the integral in order to find the antiderivative. Once we see this, we can now just take the antiderivative of the outer function, but keep the inside function intact. So let's look at take a look at another example here. So we should always do our best to try to recognize this pattern first. So I've got a couple of options here, I suppose, for what to choose for my inside function. I could see that secant x is inside of the quantity being squared. So I could see that secant x is inside of u squared. But notice that the derivative of secant x is secant x tan x, which I actually don't see because all that's attached here is a tan x plus 3. So what if we maybe choose tan x plus 3 to be the inside function? Well, notice that the derivative of tangent x plus 3 is in fact secant squared x. So secant squared x is the derivative of tangent x plus 3. So why don't we disregard that derivative, recognize that tan x plus 3 is the same as tan x plus 3 to the first power, and now we can actually apply this rule. Take the antiderivative of the outside function, which is really the antiderivative of u to the first, which is 1/2 u squared. But notice that I kept the inside function intact, and therefore this is my answer. Don't forget the plus c. Now, many times we're going to notice that the important variable part of g prime of x dx happens to be there, but it's missing a constant multiple. For instance, I could see that x cubed minus 4 is inside of a square root function. So if I were to think about x cubed minus 4 as being my inside function, I would need to see 3x squared attached to the function. Unfortunately, I only see x squared. So in a case like this, multiply the integrand, the quantity being integrated, by that necessary constant that I need. We just need to compensate by multiplying by the reciprocal on the outside of that integral. Just keeping in mind that if I multiply if I have a constant multiple inside of a function, remember that I could pull that constant multiple out of the function. So let's look at the first step. The first thing I would do is I would rewrite this in the appropriate form. Write the composition function first, which I would write as x cubed minus 1 to the negative 1/2 power, since the square root was in the denominator, times what's left. All that's left is x squared dx. So if I let x cubed minus 4 be g of x, then I should realize that x squared is not g prime of x. But in order to integrate this function, I need to see the derivative of the inside function. So note that the derivative of the inside function is 3x squared. So let's just multiply by 3. Now we see that that is g prime of x. But it seems a little odd. I can't just multiply by the necessary constant that I needed unless I compensate by also multiplying by the reciprocal. So I can multiply the inside by what I need and the outside by the reciprocal, and the reason is that 1/3 times 3 is just 1. So the integral hasn't really changed at all if I multiply 1/3 times 3. And remember, I could bring the 1/3 inside or outside based on the constant multiple rule. So now that we see that derivative, we can disregard that derivative. And we're now at a point to where we just integrate the outside function, which is u to the negative 1/2. So I add 1 to negative 1/2 to get 1/2, and I multiply by the reciprocal, which is 2. So this turns out to be the integral of the function, except remember that there's an extra 1/3 on the outside, which gives me 2/3 times that square root of x cubed minus 4. Plus c. So this is the process of pattern recognition. Recognize the pattern, meaning that we need to see the derivative of the inside function attached, and if it is, we can disregard it and just integrate the outside function. But what if we actually try to make a change of variables? So the guidelines for making a change of variables start with the fact that we have to choose some inside function. We have to choose a g of x that we're going to call u. So the most obvious choice here would be to let u equal 2x minus 1. That's our g of x. So we're now going to rewrite it as the square root of u. The problem is it's asking me to find the integral of the square root of u where the variable is x. But the variable is not x, the variable is u. So we need to change that dx as well. So the next thing we do is we find du, which is the derivative of u. Well, notice derivative of u is the same thing as finding g prime of x. So notice that du is going to be 2 times dx. So du is always going to be in terms of dx. The problem is I can't replace that dx yet, but I do need to rewrite that integram somehow in terms of only u's and du's by replacing all of my x's and dx's. So that means that I need to realize there's a dx, so solve for dx, which is du over 2. Well, when we now replace that, we now see a much easier function now, where if we pull out the 1/2, we could rewrite this now as the integral of u to the 1/2 du. This is a much easier function to integrate now because it's just a single power function, a single variable to some power. So instead of trying to recognize the pattern, we could just physically turn into u's and make the integral easier. So the integral of u to the 1/2 is u to the 3/2 by adding 1 times the reciprocal, which is 2/3. So we now just simplify that a little bit. That becomes 1/3, the 2's cancel, so we're left with 1/3 u to the 3/2 plus c. Now that is the integral. The integral symbol is gone because we have now already found the antiderivative. The problem with this is that the original function was in terms of x. So our final answer also has to be in terms of x. So we just simply replace all the instances of u with the g of x that we made in the first place. And therefore this is our antiderivative. So in this lesson we learned how to find integrals of more complicated functions that are functions within functions. But keep in mind that the only way that we're able to do that is if we see the derivative of the inside function attached to the problem. We can always check this by taking the derivative, and therefore, if I were to multiply 3/2 times 1/3, I get 1/2. Reduce this by 1 to get a 1/2 power as well. But then I multiply by the chain rule by the derivative of the inside, which is 2. So when I multiply 2 times 1/2, I get 1 times the square root of 2x minus 1. So I can always check by differentiating to see if I get back to my original result.